So,
okay.
Welcome everyone. It's a pleasure to have you all here in this very friendly seminar. I hope you enjoy today's talk. And this is a very nice opportunity for you to learn and get in contact with other researchers and other students, graduate students, and so on. So I ask you to prepare your questions to the end of the presentation. And today it's my pleasure, my honor to introduce you to Professor Noemi Wolanski. She's going to talk on asymptotic behavior of a non-local problem with absorption in RN. Professor Wolanski is a distinguished mathematician. She works at the University of Buenos Aires in Argentina. And she holds a visiting associate. She has been a visiting associate professor in Purdue University and in the University of Maryland. Her research is focused on PDEs, but it also spans to mathematical analysis in general, evolution equations and functional analysis, boundary value problems, and so on. Her contributions sum more than 1,700 citations. This is amazing. This tells us that her results are really improving worldwide things of other researchers, other students. So she has been dedicating to the advances of mathematics knowledge, and she's been actively engaged in this spreading mathematics all over the world. And we are glad that she accepted our invitation. So it's now time to start our presentation. Go ahead, Professor Wolanski.
Okay, thank you very much. It is my pleasure to be here, and thank you for organizing such a nice seminar and inviting me here. Okay, so I will start. And as the title says, I will talk about the asymptotic behavior solution of a non-local problem with absorption. The problem, we have an integral differential operator, and in the right-hand side minus u to the p with some initial conditions set up in Rn. The operator is an integral operator that you get as the integral of a kernel j evaluated at x minus y, v of y minus v of x. The kernel is non-negative, of compact support. It's not necessarily infinity, but let's think of it as being infinity. It's radially symmetric and of integral 1. And in the right-hand side, the power p is larger than 1. The initial condition is non-negative and bounded. And in order to simplify the presentation, I will assume throughout the talk that the asymptotics of the initial condition at infinity is as a negative power of the norm of the variable, even though some of the results can have a different condition at infinity. But as I will show, the time asymptotics of the solution depends strongly on the space asymptotics of the initial condition. And of course, it also depends on P and on dimension. This non-local operator appears in different applications. One of the most used is in population dispersion models. It has been used also for some image resolution methods. In the case of population dispersion, if V is the density of population, then FV will be the balance between how much is arriving at X from every point in space minus how much is leaving from X to every other point in space. How much is arriving is given by the integral of j of x minus y times v of y, How much is leaving is given by the integral of j of y minus x, b of x, but as j is radially symmetric, j of y minus x is j of x minus y. The right-hand side is modeling absorption in this setting. Now, these kind of problems, but with a local operator instead of a non-local one, have been widely studied. And for instance, if we consider the heat operator instead of our operator with the same right-hand side, we can realize what's the interplay between P alpha and N in the following way. Let's rescale the solution by multiplying by lambda 2, the alpha, and here the variable lambda x, lambda squared t. Why this rescaling? Well, the scaling of the variable is the one that leaves the heat operator unchanged. And then I will see in a moment what the scaling of this multiple lambda to the alpha y, we choose this. But why looking at the rescaling of the solution has something to do with looking at the limit of the original solution when time goes to infinity. Well, let's look here what happens if t is 1. If we put t equals 1 in u lambda, then the lambda squared is actually our time. So this lambda to the alpha is time to the alpha over 2. And the y, the variable, is lambda times x, and lambda is square root t. So if we look at the limit as lambda goes to infinity of u lambda of x1 for x in a ball of radius k, this is the same as looking at what happens with u of yt as y goes to infinity in sets of the form y less than k square root t, even multiplied by t to the alpha over 2. So, as I said, the scaling of the variables is the one that leaves the operator unchanged. And the reason why we multiply by lambda to the alpha is to keep the behavior of the initial condition unchanged. So if we look at what happens with u lambda when evaluated at time equals 0 and multiplied by x to the alpha, this is lambda x to the alpha, u naught of lambda x, and it will go to a if lambda x is going to infinity. So for each lambda, if norm of x is going to infinity, we get a. So the initial behavior at infinity is preserved under this scaling. On the other hand, for the future reference, as we will be interested in looking at the limit when lambda goes to infinity, also, if x is different from 0 and lambda is going to infinity, then lambda x is going to infinity, so the limit is a again. So this means that u lambda of x0 is conversion to a over x to the alpha as lambda goes to infinity for x different from 0. Okay, actually when 2 or p minus 1 is less than or equal n, and you notice in L1, we do not multiply by lambda to the alpha, but we multiply by lambda to the n. This is because in this way, we keep the integral of the initial condition, and the integral of u lambda times t will be the integral of u at time lambda squared t, but we keep the idea that we are working in L1. Now, the functions u lambda are solutions to this equation. So when we apply the heat operator to u lambda, there's a power a lambda squared that appears, and if instead of having u to the p lambda x lambda squared t, we want u lambda to the p, we have to divide by lambda to the alpha p minus 1. So this is the equation satisfied by the u lambdas. And looking at this equation, it becomes more or less clear that the sign of this exponent will determine what the behavior of u lambda goes to infinity is. For instance, if 2 minus alpha p minus 1 is negative, and u lambda is bounded independently of lambda, the right-hand side is going to 0, and we expect to have as limit, as lambda goes to infinity, a solution of the homogeneous heat operator. And if alpha is 2 over p minus 1, this exponent is 0, u lambda is a solution of the same original equation, and we expect the limit of u lambda to be a solution of the heat equation with absorption. And as I said, the limit of u lambda as lambda goes to infinity is related, very closely related to the asymptotic limit of the solution u as t goes to infinity. So this gives an idea of what we expect to have as t goes to infinity. On the other hand, if this exponent is positive, it is not so clear what we will have in the limit, but it becomes apparent that as this is going to infinity, absorption will become more and more important than diffusion, and that in the end, diffusion will disappear and we will only have absorption. But this is not something that is clear from the equation. Now, this problem, the case of the heat operator, was studied, but with different techniques, not with the rescaling method, even though it could have been done this way. But this technique was used for some nonlinear operators, for instance, for the porous medium equation. Now, what happens in our case where we have this integral operator n instead of the Laplacian? Well, this operator is not invariant under any scaling. But if we use the same scaling as we did for the u lambdas, then the equation looks similar to the one that we got with the Laplacian, but instead of having here again the operator L, what we have is an operator that depends on lambda, is lambda squared times an operator of the same kind, but not with the same kernel J, but with a kernel J lambda that is obtained from J by this rescaling. So if this is the case, why would it be a good idea to use the scaling method in our case? Well, the reason is that it is known that if we apply the operator L lambda to a smooth function, then as lambda goes to infinity, this converges to a multiple of the Laplacian, this multiple of the Laplacian. So that at least formally, we would expect the asymptotic behavior to be the same as that with diffusivity A. And this was indeed proved by Iñar and Ross in the case without absorption, 0 right-hand side, and by Pasotto and Rossi when you notice in L1 and 2 over p minus 1 is strictly less than m, but using different techniques and not the rescaling one. Now, if we want to use the scaling method, what are the steps that we have to follow? Well, first, we need estimates on the family U lambda uniform in lambda. In order to obtain this, we need infinity estimates on the original solution that is invariant under the scaling. Now, once we have these L-infinity estimates, prove precompactness of the family U lambda. Then, under subsequences, U lambdas will be conversion to a certain function U. Well, we need to characterize this limit function U so that we can prove that it's independent of the subsequence under consideration, so the whole family U lambda converges to U. Now, also, the characterization of U has to be used to prove, or use if it's already known, that this function, limit function U, is invariant under the scaling. So the limit function U of xt is equal to the function U lambda. And so if we look at little u lambda minus capital U lambda evaluated at time t equals 1 in a ball, the same computation that we did before, since this is going to 0 uniformly in the ball, will give that the L infinity norm of the solution U minus the limit capital U L infinity in a ball of radius k times square root t will go to 0 even multiplied by t to the alpha over 2. So capital U will be the asymptotic limit, and this is the way in which this limit is attained. These ideas, as I said before, will work well when the exponent of lambda in the right-hand side of the equation satisfied by U lambda is less than or equal to 0, and we have a limiting equation. Okay, so what are the difficulties that we find? Well, first, to find the infinity estimates. Then we find these estimates, but in many cases we find them in sets where the time is not far, but separated from the origin, from time, the initial time. So it is not so easy then to characterize the limit function U by determining its initial value, because the initial value is not necessarily the limit when lambda goes to infinity of the initial value of the U lambdas. But let's say we have these infinity estimates. Now, we need to prove that the family U lambda is precompact. Now, there are two main difficulties here. The first one is that the operator L has no regularizing effect. And of course, the rescale operators L lambda don't either. And also that the U lambdas are solutions of different operators. So this is the main difference with the heat equation. What happens in the case of the heat equation, that the rescalings of the solution are solutions of the same differential operator with a bounded right-hand side once we have bounded bounds of the U lambdas independent of lambda. The right-hand side is bounded, the solutions are bounded. As the heat equation has a regularizing effect, we have estimates, local estimates of the derivatives, and so the family is precompact, and we are bound with this thing. Now, in the case of the operator, we don't have a regularizing effect, and even if we had a regularizing effect, there's no reason why the estimates would be independent of lambda, as the U lambdas are solutions of different operators. So there's something different that we have to do. Now, as I said before, this scaling method only would work when 2 over p minus 1 is less than or equal alpha. And in this case, there are different situations. One, when 2 over p minus 1 is less than or equal dimension, and one when 2 over p minus 1 is larger than dimension. If it's less than dimension, we have one situation in which the initial condition is in L1, and this was studied by Pasotto, this which should be a Z, and Rossi when 2 over p minus 1 is less than n, and by different techniques, and with Joanna Terra, we did this in a paper in discrete and continuous dynamical systems when they are equal. Observe that if alpha is larger than n, we are in this situation because the initial condition is bounded and decays as a negative power with alpha larger than n, it will be NL1. And also remember that in that case, we don't multiply by lambda to the alpha, but by lambda to the n. Okay, the other situation then would be that alpha is between 2 over p minus 1 and n. And this is something that we studied with Joanna Terra in the same paper. And as I said before, we have an asymptotic limit that is a solution of the heat equation, homogeneous heat equation, when 2 over p minus 1 is strictly less than alpha, and of the heat equation with absorption if 2 over p minus 1 equals alpha. Now, the other situation is that 2 over p minus 1 is larger than n. This is something that we are writing right now with Carmen Cortázar from Chile and Fernando Quiroz from Spain. And actually, remember that alpha is larger than or equal to 2 over p minus 1. So alpha is larger than n in this case. So the initial condition is integrable, but we don't multiply interscaling by lambda to the n in this case, but we multiply by lambda to the 2 over p minus 1. And the condition at infinity, we write it in this way. X to the 2 over p minus 1, you know, converges to a constant that could be 0. Of course, if alpha is 2 over p minus 1, our condition is that the limit is a positive constant. And if alpha is larger than 2 over p minus 1, then if we multiply by x to the 2 over p minus 1, we would end up with a 0. So this hypothesis, if we allow a 0 constant here, then we'll consider all the possible alphas larger than or equal to p minus 1 when this is larger than n. As I said before, when alpha is less than 2 over p minus 1, we cannot use the scaling method, but anyway, we work on this problem with Ariel Salor and Joanna Terra, and the method was different, and what we did was to construct sub and super solutions with the help of eigenfunctions of the operator L, something completely different. And what we could prove is that the limit is in fact a solution of the equation just with absorption, diffusion disappears, and it's a particular solution. So independently of what the initial condition is, if it decays as a power x to the minus alpha with alpha less than 2 over p minus 1, it will we will end up seeing this function. But in this talk, I will only work and talk about the case alpha larger than or equal to over p minus 1. So in order to obtain, my idea is to give some insight of what the method is. I hope I can give you the ideas. So in order to get the infinity estimates, we have to work in different ways when n is larger than or equal to over p minus 1 and when n is less than 2 over p minus 1. The method was different. When n is less than 2 over p minus 1, recall that the scaling that we used was lambda to the 2 over p minus 1 u of lambda x lambda squared t because of the way in which we are looking at the behavior at infinity of the initial condition. So we need estimates that are invariant under this scaling. The estimates that we obtain is the decay in space is x to the minus 2 over p minus 1, the same that the initial condition has. And in time is as t to the minus 1 over p minus 1. And how do we obtain this? Well, for the first inequality, what we prove is that if the constant c here is large enough, then this function is a stationary supersolution of the equation outside a ball with radius 2 times the radius of the support of the kernel in the definition of L. Then in order to be able to use comparison, we need two things. One, to prove that initially phi will be larger than or equal to u naught, and also that in the complement of this set we have inequality. Okay, so why, if c is large, we have the inequality initially? This is because of our assumptions on the decay of u naught, and in order to get the inequality in the complement of the set is a ball, and in this ball, the function u plus x squared to minus 1 over p minus 1 is bounded below, so if c is large, it will become larger than our initial condition, and the infinity norm of the initial condition is a bound for the solution of the problem with absorption. And so comparison gives this first estimate. And in order to get the second estimate, we'll look at this function that is a solution of the equation that is independent of space. And if T naught is small enough, and the initial condition for our problem. So from the comparison principle, we get this inequality. This is larger than this for any T naught positive. And so as U is bounded, we can put a 1 here, and we have the second inequality. So this is the simplest case. What happens when the scaling is multiplying by lambda to the alpha, and alpha is between 2 over p minus 1 and n? The case alpha equals n could be that the decay is as x to the minus n, or that it is in L1, because when it is this initial condition is in L1, I said that we are multiplying by lambda to the n. In this case, in order to get the estimate, we have to work more, because we need estimates that are invariant under this scaling. The estimates that we get are similar to the ones that we got before, but with alpha over 2 here and here. And these functions are not super solutions of the equations. So we cannot use the comparison principle to get these inequalities. What we do instead is use that U is bounded by the solution of the homogeneous equation. This is the equation with absorption, is below the solution of the equation without absorption, with the same initial condition. And we can prove estimates for the solution of the homogeneous equation by looking at the representation of this solution as a convolution of the initial condition U naught with the fundamental solution of the integral differential operator. This fundamental solution was obtained by Noemi and Rossi, and they proved that it's exponential minus t times delta, the direct delta, plus a smooth function. This first term is reflecting the lack of regularizing effect of the operator. Okay, so we have this representation, and this should be UL, not U, the solution of the homogeneous equation. And when we look at this representation, we see that our assumptions on U naught and the fact that in T this is decaying exponentially will give us the estimates of the first term. So we have to get the estimates of this convolution with the kernel W. In order to get them, we need good estimates of the kernel W. When Iñat and Rossi obtained this fundamental solution, they obtained a bound for the kernel W. They proved that it decays as t times to the minus dimension over 2. But this estimate is not enough for our purposes. And so we got these two estimates for W of xt is less than or equal to constant times t, and also less than or equal to constant times t over norm of x to the n plus 2. This second estimate is the most important, because this is the one that is invariant under the scaling. That will give that this is invariant under the scaling. Okay, how do we get these estimates? By using the comparison principle for the equation satisfied by the function W. That is Wt minus Lw is e to the minus t j of x, and initially W is 0. So the first one is very easy, because if C is large enough, it's clear that W will be a super solution of the equation. Functions independent of x are, when apply L of this function, will be 0. So Wt is C, and it will be larger than this if C is large. And also it is 0. Now, in order to get the second inequality, t over x to the n plus 2 is a super solution of the equation in sets of the form x squared larger than k times t if k is large enough, and c is larger than or equal to 1. Now, if c is even larger, then in the complement of the set, so when x squared is less than k times t, this inequality that we already had will give this bound. So the comparison principle will give the bound everywhere. And in this way, we are able to prove infinity estimates. Now, in order to get precompactness, we have to work with the original function u, the solution of the equation with absorption. And what we can do is to represent u and then u lambda by the variations of constants formula, and we will end up with several terms. In order to prove precompactness with those terms, we need estimates for the derivatives of w, and so we get the equation satisfied by the space derivative and also the equation satisfied by time derivative minus e to the minus t j of x. We are able to prove these inequalities again by proving that these functions were super solutions in the right sets. Okay, so as I said before, we will use the variations of constants formula, and there are several terms. Most of them end up going to zero exponentially because of this e to the minus t delta that we have in the fundamental solution. Then there are other terms where we prove precompactness by using the estimates on grad w and wt. But there is one term for which these estimates are not enough. This term is lambda to the 2 minus alpha p minus 1, and then the double integral, the convolution of w super lambda with u lambda to the p. W super lambda is this rescaling of w. So what do we do if we cannot find estimates on the derivatives of these functions? We look at something that looks rather similar, but instead of having the kernel w lambda, we have as a kernel here the fundamental solution of the heat equation with diffusivity A. Why? Because it is known that w lambda converges to this fundamental solution, and it converges in such a way that we can prove that this difference going to zero uniformly on compact sets. So if we prove precompactness of this family, we will have precompactness of our original family. Why do we have precompactness of this family? Because these functions are absolute bounded, because this power is less than or equal to zero and lambdas are bounded, are uniformly bounded solutions of the heat equation equals this power of lambda times u lambda to the p. Right hand side is bounded, the solution is bounded, we have bounds of the derivatives, and so this family is precompact, and thus this is precompact. So after all this work, we have precompactness, and so we know that under subsequences we have conversions to functions u, and it is immediate once we have these uniform conversions on compact sets that these limit functions u have to be solutions of the heat equation, the homogeneous heat equation if alpha is larger than 2 over p minus 1, and of the heat equation with absorption if they coincide. And this is done by looking at the weak form of the equation satisfied by the u lambdas and using that the scale operators L lambda applied to test functions will converge to A times Laplacian of the test function. Okay, so in order to characterize u, we need to find what the initial condition of u is. And at this point, there is a big difference depending on the relations of alpha p and n. Okay, when 2 over p minus 1 is less than or equal to n, and either you know this in L1 or alpha is between 2 over p minus 1 and strictly less than n, then u lambda initially converges in the sense of distributions. The case alpha equals Z requires a different scaling. I will not discuss this case here. Anyway, it is not true that capital U of x0 is the limit of U lambda of x0 always. For instance, if you know decimal 1, then U lambda of x0 is conversion to m times the delta function, where m is the integral of U naught. But what we prove is that the initial condition for capital U is a constant that depends on U times delta. And this constant is the initial integral minus this integral, double integral here, and this is the final mass of the solution U. So it is not the limit of U lambda of x0. It requires work, but this is what the limit is. On the other hand, if alpha is between 2 over p minus 1 and strictly less than n, then the U lambdas are converging to a over x to the alpha in the sense of distributions. And in fact, we can prove that U of x0 is a over x to the alpha. But in order to prove these results, we need some estimates on integrals starting from 0, because the convergence says t than or equal to no positive. I will not discuss how we do that. Now, uniqueness of the solution of these problems, the problem is either heat equation, homogeneous heat equation, or heat equation with absorption, initial condition multiple of the delta, Dirac delta, or initial condition A over x to the alpha. So these problems have initial conditions that are measures, non-negative measures, non-negative solutions with initial conditions that are non-negative measures. For these equations, there is uniqueness. And this, since the initial condition is invariant under the scaling, this means it gives that the solution is invariant under the scaling. And so this ends the proof, because as I said before, once you have characterized the possible limits, then you know that this limit is what is giving the asymptotics. Now, what do we do when 2 over p minus 1 is larger than n? As I said, our assumption was that x to the 2 over p minus 1, you know, converges, you know, of x, 0, you know, the xt converges to a non-negative as x goes to infinity. And so, for instance, when a is positive, U lambda initially is lambda to the 2 over p minus 1, you know, of lambda x is converging to ax to the minus 2 over p minus 1 if x is different from 0. And this it does not define a distribution, because 2 over p minus 1 is larger than n, so this is not locally integrable. So we have to do something different. And it's even worse when a is 0, because in that case, lambda to the 2 over p minus 1, you know, of lambda x is going to 0 if x is different from 0. So the first thing is that we may think is that we have in the limit the 0 function, but this is not the case, because we can prove that the integral of the limit function as t goes to 0 goes to infinity. So this limit, capital U, in the case a equals 0, is what is known as a very singular solution of the heat equation with absorption. Now it's known that there is a unique, very singular solution, and that this solution is invariant under the scaling. So all that we discussed will give that this is the asymptotic limit in this case. Now, how do we prove that U is a very singular solution? How do we prove that the limit as t goes to 0 of the integral of U is infinity? Well, what we do is we construct a lower bound for U lambda that is a solution of the rescale non-local equation with absorption. So the same equation that U lambda satisfies, but has an initial condition integrable with integral arbitrarily large that is below the u lambda of x0 if lambda is large. And so the integral of u lambda of xc will be larger than or equal the integral of this lower bound v lambda of xt. We use estimates that we have on W in order to be able to get the integrals of the v lambdas are larger than or equal something that converges to lambda, and in this, as t goes to 0, and in this way, we prove that the limit of u is larger than or equal L, and as L was arbitrarily large, we have the result. Finally, what do we do when A is positive? Okay, so we know that if there is a unique solution of the heat equation with absorption that converges to this function as t goes to 0 if x is different from 0, and moreover that this solution is also invariant under the scaling, so it is at the asymptotic limit. So how do we prove that capital U of xt converges to this function as t goes to 0 if x is different from 0? What we do is we construct sub and super solutions for the u lambdas that are defined in a neighborhood of x0. X0 is at any point x0 different from 0, and these sub and super solutions initially close to x0 take this value, the positive limit function plus epsilon for the super solution and minus epsilon for the subsolution. So the u lambda is between the subsolution and the super solution, and not only u lambdas are converging to capital U, but we can prove that the subsolution and the super solution that we construct are converging to a function that is continuous up to time t equals 0, and take these values when t goes to 0 and when they are evaluated at x0. So u of x0 t is the lim inf is larger than or equal this, the lim sub is less than or equal this, as epsilon is arbitrary, the limit is this function. So, okay, so I hope that I gave you an insight of the proofs. It's very technical and different techniques, but maybe something ends up floating in the air at the end, and I thank you very much for your attention.
Thank you very much. Indeed, I loved learning this new technique. It is something new for me, this rescaling method, and how you get the rescaled equation and kind of overcome the problem that you have. And I loved it. Thank you very much for your presentation. I would like to know if any of you have any comments or questions to Professor Noemi. I have just one comment. In the beginning, you mentioned that the integral of that j there in the very beginning would be like 1. This could be viewed as a kind of probability or something like that for you to...
It's exactly that. It's a probability distribution of something arriving at a point x from any point y in space.
And have you been using these techniques in other kinds of equations?
Well, the scaling method is used in many equations. In any equation where that is invariant under scaling, you can think of a problem of looking at the asymptotics in time by looking at the limit of the rescaling functions as the scaling parameter goes to infinity. And this has been used in many problems, and we used it in many problems. The idea that was maybe new was to use it in this problem that is not scaling invariant. But as in the limit, the scale operators converge to the Laplacian, then you can use it with more technical difficulties, but you can use it in different problems. We used it to look at the problem in an exterior domain, for instance, what the asymptotic is in an exterior domain. But it's been used a lot well before we started working with the problem.
Yes, it's very nice. I like paying attention to the techniques when people are presenting things, because then we learn how to overcome our difficulties. This was awesome. Thank you very much for your talk. Anybody else?